All right, so we've talked about the general CRD model. We've also talked about making contrasts using the effects from that model. We've also now talked about multiplicity corrections and summarizing our model results, making sure we use an appropriate multiplicity correction when reporting multiple effects from the model. So now we're going to talk about, take a step back and go, okay, let us assess the assumptions of our models that we're using in this context and make sure that we have models in the proper form and can validly report results from these models. So in a basic CRD model, we assume the following, that each response, Y, ID, is modeled using a grand mean, the effect, alpha I, for each level I equal 1 up to G, and there's error associated with these. Now it's important that these error terms be independent and normally distributed with a constant variance. When these hold and matches our model design, our study design, then we know we're good to go. We need to be able to know that this holds, though, and making sure that we validate that each time. When the assumptions aren't true, our inferences might not be valid. Now, not all the time, honestly, but much of the time, if we have applied incorrectly the statistical model, we will get results that are spurious. So a confidence interval may not be actually covering a stated error rate. You might say 5% error, but it might be much, much greater or much, much smaller. A nominal error rate of epsilon could actually have a higher or smaller error rate similarly. This is obviously not good, and part of what we spent the first part of the class talking about inconsistency, reproducibility issues in research studies, and perhaps some of that can be accounted by not properly applying the right model. There's a lot of people out there that go, oh, well, the ANOVA robust or the ANOVA model is robust to non-normality, and that is true when you have just maybe heavy tails. But if you have highly skewed data, discrete data, other things like that, and you're applying a one-way ANOVA general linear model format, you really are on the wrong track and need to go take, say, a categorical data course or know other kinds of functional methods to appropriately model your data. Of course, we'll talk a little bit later about randomization inference, and if you do that, then you don't have any of these validity issues. I wanted to make sure we covered this, though, before we get to this, because it seemed kind of backwards to me. But we will go back. Some procedures work reasonably well, even when some of your assumptions are violated. So that's what I meant before when I said many people say the ANOVA model is robust to non-normality and other assumption violations. This is called the robustness of validity. Generally, these procedures work because if you just have a very mild violation, it's not going to affect the validity all that much. But it may not be the most efficient way to go about it. And so you always want to think about the data and actually the data you're trying to model and not just think, oh, can I make this model that maybe isn't ideal work? I don't like that approach, the second approach. So our basic assumptions are independence, constant variance, and normality, just like in regression modeling, because this is just a linear model, just like a regression model. There's lots of ways that we can fail in all of these, including independence. We're not going to go into methods for fixing or accommodating to dependence in the response. That is more appropriate for other courses. All right. Here's a little note Gary wants to make about how bad is it really if we violate assumptions. Skewness, if you recall, measures how asymmetric a distribution is. Kurtosis measure how long-tailed or outlier-prone a distribution is. And the normal distribution has 0 skewness and 0 kurtosis, because remember, it's perfectly symmetric unimodal distribution. Apart from having really extreme outliers, that F-test is only very slightly affected by non-normality, so it really is resistant. Um, but individual outliers can change the test results. So, part of that exploratory data analysis that we have been doing is really to figure out, do we have some strange observations that we need to think about as we start picking the appropriate modeling strategy or not? You can always check with and without outliers to see if if you get a consistent result. If so, I just leave them in, state it, and move on. For balanced data, the case that all sample sizes are equal, which recall we don't need, skewness only has a small effect. Long tails, i.e. positive kurtosis, will lead to very conservative tests. The p-values are going to be larger than what we would really need, or they should be, and so we'll not make as many rejections. We won't have as many significant effects, versus short tails leads to liberal tests, so that we'd be more likely to make rejections and maybe have some spurious results. Let's take a look at table 6.5 in just a moment and see some of these results. Actually, I think it's 6.4. There is a mistake here in the notes. It should be 6.4 there. I just looked it up because I had my doubts. Here we have skewness. This is skewness. This is kurtosis. The formulas for these appear in the textbook. They're really just higher order moments. So it's the centered moments, I should say, higher ordered centered moments for the distribution. So if we have normal, we know they should both be 0. This is the third centered moment, the fourth centered moment, with it being rescaled and recentered in the kurtosis measure in particular. For uniform, because we do have the heavier than expected tails, we see this negative value. For normal truncated, we get lighter tails. I should have said lighter tails there. If we truncate at plus or minus 1 standard deviation, that should be 1 standard deviation there. For a student T distribution with only 5 degrees of freedom, we're going to have heavier than normal tails. So we get a big positive value there. When we get up to 20, it's getting closer and closer to 0. Notice how it just continues to get closer to 0 as our degrees of freedom get larger. For chi-square, these are the values. This is a non-symmetric distribution, decidedly. So we see really different values for the measure of symmetry there. Okay, just guidelines. You're not really going to be responsible for this, but if you really suspect non-normality and you see something that kind of aligns with these, sometimes I find that useful to kind of match up those moments. There are actually functions in R which will do empirical distribution function fitting for you if you're really interested, but that would be way beyond what we're going to do in this course. Okay, so here's the actual type 1 error rates for F-tests. If we're assuming 5% for various values of skewness and kurtosis using the methods of Guyan here. Again, just to show you, yeah, we really do deviate some for these varying measures, but notice we're assuming 5% error rate. Here we get conservative because we have positive values for kurtosis, and here we tend to get a little bit liberal. If we have varying sizes of groups and varying levels of skewness, or this level of skewness and kurtosis, we'd see the following errors. Also, just to show you that it really does matter at some level, we see quite a liberal error rate there. So the skewness appears to be really a problem, particularly with the one-sided intervals. And two-sided intervals are less affected by skewness, but the coverage may pile up on one side because of the skewness, exactly. Pairwise combinations with balanced data are doing okay, and the differencing tends to cancel out that skewness, so it tends to look all right. On the other hand, non-constant variance can have really serious effects, but the effects are smaller if you have balanced designs, so equal sample sizes within each treatment group or treatment level. So if your big sample sizes, so NI recall is a sample size for a treatment group, if that corresponds with large measures of heterogeneity, large variance estimates, you're going to get a conservative test that doesn't reject effects enough, because the big variances are overrepresented and inflate that MSE. So that's going to inflate your MSE. We're not going to find effects that are truly in the data. If the big N's go with small variances, then we'll get liberal tests. So we really do want to, this one to me stands out as a really important thing to check, and we'll be doing this in class and seeing the mechanics of doing the checking for heterogeneity of variance across the levels. I like graphical methods. I'm not a big fan of numerical tests for this, but I really like the graphical methods. Let's look at the table in the text about how bad things can get if we violate non-constant variance. We're doing in this table 5% tests that actually vary from 3% to 20%. So that's the one I worry about. That whole normality thing, I'll often tell you guys, oh, don't worry about that so much, because again, like I just said, this is the one that really causes headaches. Okay, thankfully it's often easy to fix too. So more data doesn't fix the problem on this, right? So it's not like we're shooting for asymptotic normality and getting more data will help here. Getting more data doesn't presumably change much at all. So we really do have to think about transformation. And we'll talk about things like Box-Cox and other variance stabilizing transformations that are really effective. For pairwise comparisons, some are going to be liberal, some are going to be conservative. So here's that table. It's printed in its entirety in your book. You might pause and go look it up. I think it's kind of a little bit after 6.4, table 6.4 in your book. So here we see, remember, we're shooting for 5% error rate. We see error rates up to almost 10, almost 20, over 20 here. This is, so notice the treatment groups are given here. So here we have the varying levels of variation for treatment and the sample sizes per group. So we can see, you know, when we have balanced data, it can get bad, but not super bad. And these are all the balanced data cases. But when we have unbalanced data and we have a lot of heterogeneity and variance, things get real bad. Okay, so watch for this. This is the one I'll really talk about and spend time on in class. Outcomes with dependent data require other kinds of models. That's all I'm going to say about that. If we see dependency in this class, it may be due to time, in which case you need time series. It may be due to clustering, in which we need hierarchical modeling. There's a multiple of reasons that we're seeing dependency in the responses, and it just requires more sophisticated modeling. Hopefully we haven't induced dependency by improper randomization. That is something we hope that we've taken care of by this point. For example, that preliminary example from early chapters where we talked about that they didn't randomize the order of the processing in the lab, and so there was dependency that had nothing to do with the experimental factors, and that in that case your data is useless, unfortunately. In this case of dependency too, more data doesn't help, but randomization, like I just talked about, does. So we want to make sure we randomize well in all cases.